particular time zone. I'm Dr. Cameron Van Eck. I am a research associate at the University of Toronto, specifically at the Dunlap Institute for Astronomy and Astrophysics, where I work as a professional astronomer, a radio astronomer, working on research into cosmic magnetism. And so I was sort of invited to give a talk, and this is a talk that I sort of had stashed away. This is a talk I'd previously given to both public audiences and undergraduate audiences, covering sort of just some of the basic ideas of what radio astronomy is and what we do with it. And so I'm sort of vaguely aware that you've had a seminar before on radio astronomy, so there may be some repetition in this, but hopefully there is some new material as well. And so by all means, please interrupt me with questions if anything pops up that catches your interest or is unclear. I'll try and monitor the whiteboard chat channel as well, although I have to turn my head to do so, so I may not catch new questions right away. So do feel free to interrupt me. Yeah, I guess we can just jump straight in. So I've sort of divided this into four sections, sort of beginning with motivating why. Why is radio astronomy interesting? Why do we do it? And then a section on natural sources of radio emission. So what are we actually looking at when we're detecting radio emission from outer space? A very brief section on radio telescopes and sort of some of the principles of their operation and some of the different designs that exist. And then a quick tour through a couple of the science cases for things that we're doing with radio astronomy, highlighting mostly the ones that I find most interesting. So it's not a comprehensive tour, I should say, but it is designed to fit within a seminar time slot. So given what I understand about this audience, I probably don't need to introduce the electromagnetic spectrum in any great detail. In the sense that we know that there are a wide range of frequencies, wavelengths, energies. So of what we essentially treat as different categories, even though it is sort of a continuous range going from the high energy gamma And so all of these are interesting for doing astronomy, as the different energy ranges, the different frequency ranges are associated with different aspects of physics. And so by observing astrophysical objects across the entire electromagnetic spectrum, we gain far more information about the physical processes involved. And so the more of the spectrum that we can cover, the more we learn. So what makes radio particularly interesting about this is the property of atmospheric windows here on the Earth. And so here I have sort of two different versions of the same plot, which is atmospheric opacity as a function of different wavelengths of light. And so this is essentially measuring how much the Earth's atmosphere is blocking light from space from reaching the ground, where 100% is everything is completely blocked, 0% is a completely transparent atmosphere where everything reaches the ground. And so immediately you can see the optical regime marked by the rainbow here, and this is a very transparent part of the electromagnetic spectrum for the atmosphere. The vast majority of light from space does in fact reach ground level in the optical, and that's why we're able to see stars, galaxies, the sun, the moon, everything else with our eyes. But the rest of the spectrum tends to be a little bit more messy. And so in sort of the higher frequency regime, going to the left of the optical, the atmosphere is highly absorbent of far ultraviolet, X-rays, gamma rays. And so this regime is entirely dependent on space-based detectors to be able to do any astronomy, since there is no signal left at ground level. And then going to the lower energy regime to the right, the infrared is a bit of a mess. There are some infrared bands in which you can do astronomy from the ground and get meaningful signal. And then beyond some point, things tend to just become completely opaque, and you're again sort of reliant on satellites to collect data in the far infrared. But as you keep going to longer and longer wavelengths, a second good window opens up, and the atmosphere becomes completely transparent to radio emission across a very, very wide range of wavelengths. And so this is you can immediately see from this plot, this is more than a factor of 100 in wavelength. And you know, for reference, the optical window here is about a factor of 2, and then a little bit further into the infrared. And so this is a very wide window into space, which allows us to build radio telescopes on the ground, so saving us all the cost of the rockets and sort of the difficulties of manufacturing satellites. And so you can either build a radio telescope much more cheaply than you can a gamma ray or a mid-infrared telescope, or for the same budget, you can build a much, much more powerful instrument. And so the radio window here is actually limited by 2 physical processes, essentially. On the high frequency side, on the left here, we're essentially limited by water vapor primarily in the atmosphere. And so water vapor has a lot of absorption bands. And so it tends to very broadly absorb sort of millimeter band radiation. And so you can actually push this end of the window up to sort of higher frequency, shorter wavelengths by going above the water vapor. And so there are a number of very high frequency telescopes located essentially above the cloud layer in places like the Atacama Plateau in Chile, the Mauna Kea volcano in Hawaii, and also at the South Pole, where all the moisture has simply been frozen out at the South Pole telescope. And so there are ways of getting around this upper limit. The lower limit, by comparison, is caused by absorption in the Earth's ionosphere, this being the layer of plasma above that sits sort of in the upper layers of the Earth's atmosphere. It's a layer of plasma, and plasma has the property of being very absorbent to low-frequency radiation. So there is some low-frequency limit that depends on the state of the ionosphere, the density and such, below which the ionosphere becomes incredibly absorbent to this radiation. And so this can move back and forth a little bit depending on the ionospheric conditions and how much the sun is ionizing the upper atmosphere. But ultimately, that's not something we can really avoid. And so that really sets sort of the hard lower limit of what we can do for radio astronomy from the ground. So we have all of this enormous window to play with for doing astronomy, except other people want to use it too. And so because the Earth's atmosphere is fantastically transparent to this wide range of frequencies, people want to use it for communications and other purposes. And so we don't actually get all of that window to ourselves. And so this is actually a chart of how the frequency spectrum is divvied out or has been assigned commercial use, in this case in the United States. And so every country has essentially declared each part of the radio frequency range can be used for some particular purpose, and it's been allocated what that purpose is, and in some cases even which companies are allowed to use particular frequencies. And I mean, as I said, it does span an enormous range of frequencies. So each, except for the very top panel, each of these is a factor of 10 in frequency. And so we have here easily 6 orders of magnitude to play with. But out of all of that, only the yellow boxes are reserved for astronomy use, which is to say, in these yellow boxes, no one is allowed to transmit. And so they're protected for astronomers to be able to have clear views of the sky at those frequencies. And as you can see, that's not a lot of frequency coverage. It's kind of terrible. And so what we essentially do these days is we observe at all frequencies, and we have to do, put in fairly considerable effort to avoid or remove man-made signals across the entire frequency band. And so there's a number, I've listed here a couple of the more obvious or more common sources of man-made radio frequency interference, and sort of at their typical frequencies. And so we can observe, in principle, at any frequency, but it becomes an interesting question of how badly are we affected by man-made signals. And some frequencies it's better and some it's worse. And so, despite these difficulties, we do observe essentially the entire radio range. I've marked here in orange all of the frequency bands at which I could find at least one radio telescope operating. And so this goes all the way down from the lower limit set by the ionosphere all the way up to essentially as high as we can go. And I've also marked in green here just the particular bands and instruments that I've worked with over my career. And so it's a couple of different instruments. And so this essentially summarizes our motivation for what makes radio astronomy significant as a part of astronomy, which is we can do it from ground level. We have all of this sort of multiple orders of magnitude of the electromagnetic spectrum that we can work in. And so there's correspondingly a very large range of physics that we can explore in the radio regime. Any questions on that before I move on to the next section? Yeah, all right. So yeah, as I said, feel free to interrupt me or put your questions in the whiteboard chat. So yeah, now I want to introduce a little bit some of the natural sources of radio emission. Because a lot of people, members of the public and particularly, get this idea that we're either listening to aliens, listening to transmissions from aliens, or that we're operating some kind of like a radar system where we transmit and then receive reflections. And while there are searches for alien signals and there are the occasional radar-based project, the vast majority of radio astronomy is looking at naturally occurring radio emission of various types, and then classifying the different types and figuring out what the underlying physics is associated with that particular type of source. And so what are these natural sources? And so people who have done a bit of physics will probably recognize a few of these, particularly this first one. The first one is simply thermal radiation, the sort of also called black body radiation, or you might have encountered this idea of how heat radiates in the infrared. And so you can get things like infrared cameras and the like. And so this is very, very popular physical phenomenon, but it doesn't stop at just the infrared or at things glowing red hot, yellow hot, white hot, in the visible regime. Blackbody radiation continues on. This is now a plot in frequency space, so radio is on the left. And so blackbody radiation does continue all the way into the radio regime, albeit relatively faintly. And so in principle, it is possible to detect thermal radiation from sources, although the spectrum is comparatively steep. And so I've marked here in the radio regime, it's almost always following this frequency squared law. This is, people who have done some physics, you may have heard of the Rayleigh gene. I think it's Rayleigh gene, yeah. Rayleigh gene tail in the blackbody distribution. And so this is what we're seeing here. And so regardless of the temperature, you get this frequency squared law in the radio regime. And if you observe at high enough frequencies, it can be bright enough to detect for some sources. The second category of natural radio emission is atomic emission and absorption lines. And so you may have seen these, again, sort of in the optical regime. If you take a spectrum of, you have some background source and you shine it through some colder gas, you can get these absorption lines. If you get hot gas, you can get these emission lines. This is hydrogen gas in this example. And these lines are associated with transitions between different quantum states in the atoms, where with each different transition corresponding to a different amount of energy and corresponding a different color or a different frequency of light. And so these are seen quite broadly in optical. This is an example of a spectrum of the sun. And so you can see an incredible number of absorption features from different atoms, and in some cases even a couple of simple molecules. But this phenomenon is not just limited to the optical. You can get this in the radio as well, but since radio emission corresponds to very small energy levels, or very small energy gaps, correspondingly, that means that absorption and emission lines in the radio correspond to very small changes in energy levels. And the most famous of which in the radio is this emission line of neutral hydrogen gas at a frequency of 1420 megahertz, or a wavelength of 21 centimeters. And so this is the infamous 21 centimeter hydrogen line. And this is associated with two energy states differentiated by the spin of the electron, actually, in the ground state of hydrogen, where the energy state where the spin is parallel to the proton spin has a marginally higher energy level than the corresponding state where the spins are anti-parallel. And so it's possible then for a hydrogen atom to undergo this state transition where the electron flips its spin. And the energy difference of this is incredibly small. And so just in order to sort of make this jump from this energy, it corresponds to a temperature of less than 1/10 of a Kelvin. And so any hydrogen gas in the universe is hot enough to excite this state, and so to have a population of atoms ready to make the transition. And because the energy difference is so small, the sort of average lifetime before a given hydrogen atom undergoes this spin flip transition is 10 million years. And so essentially, if you have a population of hydrogen atoms anywhere in the universe, for any given atom, if it's in the excited state, which is usually 50-50, once every 10 million years, it will give off a radio photon. And if you have enough hydrogen, you produce enough radio photons that this becomes a detectable signal. And so you get a emission line where if you look at a radio spectrum towards some particular source that does contain a lot of neutral hydrogen, you get a clear emission line. And even better, because the frequency of this emission line is subject to Doppler shifting, we can now extract information on the velocity of the hydrogen gas that's creating this emission. And so this becomes a very powerful tool now for studying not just where hydrogen is and how much there is, but also how it's moving. And so here's an example of such an observation that can be done through amateur radio astronomy. This is some data provided by Apostolos here. And you can see in the top center panel, this is a hydrogen spectrum through the plane of the Milky Way, if I recall. And you can see, as a function of different frequencies corresponding to different Doppler velocities, different amounts of hydrogen emission. And so this contains a lot of information about the structure of hydrogen gas in the disk of the Milky Way. And so there's a lot of fantastic things you can do with these kinds of observations. But hydrogen gas is not the only gas that has emission lines in the radio. Particularly if you go to much higher radio frequencies, you reach a regime where many different kinds of molecules have emission lines or absorption lines as well. And so on the left side here, this is a spectrum taken at very high frequencies of the Orion molecular cloud, and people have been able to identify many different kinds of molecules that are now present in this cloud and emitting. And so there's probably, I don't see it labeled here, but there's usually water is found, hydroxyls, methanols, ethanols even, but also, sulfur compounds here, sulfur monoxide, sulfur dioxide, formaldehyde. I've seen, many other sort of simple organic molecules and non-organic molecules. And so you can learn a lot about the composition of things by studying these molecular lines. And as I said before, you can also get sort of the Doppler kinematics. And so you don't have to do this simply for one particular direction, is you can do this in a resolved way. And so here's the Whirlpool galaxy M51 on the right here, where we can see this is the carbon monoxide molecule traced out across this galaxy. We can see where it's present, how it's concentrated into the spiral arms. And in the right plot, we can then see its velocity, the velocity of this carbon monoxide gas. And you can actually see elements of the rotation of this galaxy and sort of work out kind of the inclination of this galaxy relative to our line of sight and how it's rotating. And so there's a fantastic amount of information encoded within these spectral lines. The third type of emission relevant at radio frequencies is called Bremstrolung or free radiation. And this is a form of radiation that is associated with dense plasmas, where you have electrons that are decoupled from their nuclei, flying around, just undergoing thermal motion, and periodically, or some part of the time, these electrons will have close interactions with the positive ions in the plasma. They'll experience basically an electric field coming off the ion and be accelerated in that electric field. And classical electrodynamics tells us that whenever an electric charge is accelerated, it will produce radiation. And so just this process of having electrons flying past ions and having their trajectories bent or accelerated will produce low frequency radiation. And so you end up with a slightly complicated broadband spectrum, where at some regime, at the very low frequency regime, you get the effect where the plasma actually starts to reabsorb the emission. As I mentioned, in the case of the ionosphere, plasma likes to reabsorb low frequency radio emission. And so you get that kind of behavior, and it actually, combination of emission and reabsorption, that actually starts to behave a little bit like a black body. And so you get the same kind of frequency squared black body spectrum. And then at some point, the emission is able to escape past the plasma. It doesn't get absorbed efficiently, and you get this very flat spectrum. And then at the very high frequency or high energy regime, you don't have electrons with enough energy to radiate at high frequencies, and so you start getting sort of a classic thermodynamic cutoff. This is a very characteristic kind of shape associated with plasma, essentially anywhere in space, although the strength of this radiation really strongly depends on the density, because it's essentially a product of these interactions. And so the more dense the plasma, the more the electrons and the ions are coming into close contact and having this process.
Can you elaborate on the greater frequency region? Like, why is it cutting off?
You mean at the high frequency end here?
Yeah.
It essentially boils down to how much energy is available to the electrons. And so these electrons are, at least so far as I'm aware, approximately in equilibrium, thermodynamic equilibrium. They have some characteristic temperature, and that means they have some characteristic kinetic energy. And so the upper limit for how much energy you can get in the radiation is basically whatever the energy of the electron is. If it loses all of its energy in one interaction, that's the most energy you can get into the radiation in one go.
Okay.
And so that effectively sets the upper limit.
Got
it. It's making me a sec. My throat's dry. All right, thanks. So yeah, and so the final form of radiation I'll discuss today is synchrotron or cyclotron radiation. And so, as I've mentioned, previously, when you have free charges that are accelerating, they produce radiation. And so in Bremstrolung, it was free electrons, thermal electrons, being accelerated by the electric fields of nearby ions. In synchrotron radiation, the force comes from ambient magnetic fields, and so whatever magnetic fields happen to be present in the astrophysical environment. And the electrons, there are a couple of different electron populations. So thermal electrons tend not to radiate very much power from magnetic fields. In that case, in the low frequency regime, it's cyclotron radiation. and it tends not to produce very much power. But there's also a population of incredibly fast electrons from cosmic rays. And so these are electrons that are essentially just under the speed of light. And if you think back, if you've done any electrostatics, the force produced by a magnetic field is the velocity times the magnetic field strength with some vector terms as well. And so the velocity times the magnetic field strength, and so these relativistic electrons at nearly the speed of light experience much, much stronger forces from the magnetic field, much stronger accelerations, and correspondingly produce much, much more radiation. And so this is synchrotron radiation, where these energetic cosmic ray electrons spiral around the magnetic fields in space and give off radio emission. And so again, the spectrum has a very similar kind of shape. It has at the low frequency regime, it has this self-absorption phenomenon. And then at some point it becomes more transparent. You have a power law of some kind, and the slope actually depends a little bit on the properties of the electron, the cosmic ray electron population, depending on how the energies of the different electrons are distributed. You can get slightly different slopes, but it's always a negative slope, and in some cases quite steep. And then at some high energy regime, you kind of just run out of available energy. And so there's a couple of interesting consequences to this. And so because this tends to have a very steep negative slope, it means it becomes brighter as you go to lower and lower frequencies. I mean, over to some limit, which depends on the exact physical conditions. And this is quite different from the thermal radiation and the free radiation, which was more flat. And so you can immediately classify the radiation based on the spectral shape. And so broadband emission, if it's flat, it tends to be generally free. You can get flat synchrotron in some conditions, and so that makes things a little bit more difficult. But if it's a steep negative spectrum, you know it's synchrotron. If it's a positive slope of 2, you know it's probably thermal. And so this immediately gives you a lot of power to understand the physics of your environment immediately just by measuring the radio spectrum. And so to give an example of this, here's a map of a part of the galactic plane made by a telescope called the Murchison Wide Field Array in Australia. And they've observed at 3 different low-frequency radio bands, and then colored it red, green, blue, corresponding to the energy or the frequency of each band. And so purely from the color alone, you can begin to classify different kinds of radio sources by their spectrum. And so you get some class of radio sources that tend to be much more reddish, indicating that they do have more emission at low frequencies and very much less emission at the higher frequencies. And so these are synchrotron radio sources. In most cases, these are actually probably supernova remnants. And there's also some population of bluer features. There's actually a very clear one here, there's a couple over here. And so these are objects that are producing a lot more high energy radio emission. And I think because of the way they've set up the color balance, they're probably not thermal, where they have much more high frequency emission than low frequency. It's probably actually, these are probably more flat spectrum sources associated with Bremstrolung emission. And so these blue regions are dense plasma clouds in the interstellar medium. And these are dense plasma clouds associated with very hot ultraviolet emitting stars. And so the very hot young stars, they emit a lot of ultraviolet. They ionize hydrogen gas in the nearby interstellar medium, producing these high density plasma pockets in interstellar space. And these then produce the Bremstrolung radiation, and we see them in this particular image as these blue blobs. And so with this kind of data, you can immediately start to classify different things based on the physics of their radio emission. Are there any other questions about sort of the radio emission physics before I move on to the telescope section?
Yeah, I have one question. So most molecular clouds when located in space near us consist of mostly hydrocarbons, yes?
So the molecular clouds in terms of composition, they're primarily hydrogen and helium. So they follow the standard abundances that we expect from stars and other other nebulae and stuff. So yes, primarily hydrogen and helium. But hydrogen and helium, I mean, helium by itself doesn't have a whole lot of interesting lines, particularly in the radio. Hydrogen, if it's atomic hydrogen, we can pick it up at the 21 centimeter line. But if it's molecular hydrogen, H2, it actually, that suppresses the 21 centimeter line. And due to some aspects of quantum physics, H2 molecules don't actually give off very much radiation. They don't have very many spectral lines. And so it's hard to actually see hydrogen molecules. And so there's actually been, this is a side note, there's been a lot of studies that have worked out the link between carbon monoxide and hydrogen molecules, H2. It's been found that usually there's a fairly fixed ratio between the amount of carbon monoxide and the amount of molecular hydrogen. And so what a lot of people have done now that that's been understood is you can go out and you can do these carbon monoxide measurements, which are comparatively easy now because apparently carbon monoxide is a really common molecule in space because I guess it's really easy to form. Even though carbon and oxygen are not super prevalent, like there's not a lot of them in the clouds, but they form this molecule really, really easily. And so people go out and they measure the carbon monoxide and they say, okay, we know for every carbon monoxide molecule there are whatever the number is, 1 million or something, hydrogen molecules. And so you can work out how much hydrogen is in the cloud even though you're not detecting the hydrogen. So there's a lot of stuff like that goes on. That was a bit of a diversion from your question, but I hope I answered your question.
Yeah, thanks.
Sure. Yeah, all right. So let's talk a little bit about radio telescopes, I guess. Radio telescopes come in a lot of different sizes and shapes these days, but the underlying principles do tend to be the same. And so here I've shown 3 different examples of what they can look like. And yes, 3. This is a bit of a trick. There is a third radio telescope here that isn't obvious if you're just looking at the image, if you don't know what you're looking for. And so at the top here, of course, is the Effelsberg 100-meter dish, which is a very classic radio telescope, satellite dish kind of construction. This is what you kind of maybe expect. On the right is the Chime telescope, which is somewhat more unusual. It's not a dish, it's this sort of half-pipe parabolic cylinder shape. And so instead of being circularly symmetric, it's got this cylinder geometry. And then thirdly, in the bottom of this left image here, is a piece of a telescope called Lofar, the low frequency array. And it's a bunch of sticks and wires, and I'll come back to that in a moment. And so, the underlying physical processes of all of these are the same, but there are different sort of design choices you can make depending on how you want your telescope to work. I mean, so the fundamental basic principle is basically you need an antenna. And an antenna is essentially anything that converts a incoming electric field associated with an electromagnetic wave, and it converts it into a voltage in whatever circuit you've attached it to. And so on the left here, here's some images, courtesy of Apostolos here. So on the inside here, we have this little copper rod, and that's all you need for an antenna. Just a little piece of metal wire or something. And so the electromagnetic radiation that's coming in is getting absorbed by the wire that's connected to a circuit, which then goes on with amplifiers and detectors, etc. And so essentially, this is any device that makes this conversion from an incoming wave to a voltage in a circuit is what you need for an antenna. And that's really the fundamental aspect of what you need for a radio telescope. Is something that takes an incoming signal and puts it into your electronics for you to be able to work with and process and store. And so the purpose of sort of the classic dish construction that we associate with a radio telescope is essentially the exact same purpose that you have for a lens or a mirror in a classic optical telescope. And so it basically serves 2 purposes. The first is that it increases your collecting area, and so all of the light coming in across the entire area of your dish gets focused into a single point where you can detect it. Thus, you get more signal at your antenna. Excuse me. And the second effect is that it actually improves your resolution. And so any optical system, whether it's a optical telescope or a radio telescope or anything else, is subject to diffraction of light. And diffraction is stronger when you have sort of smaller and smaller apertures of light. And so this affects your ability to differentiate emission in sort of slightly different directions. And so you can actually work through this. If you go through sort of the wave optics, diffraction dictates that your resolution, your ability to differentiate sources based on their different directions, scales as the wavelength divided by the diameter of your optical system, so which is usually the main mirror or the main dish. And so in the optical regime, this is not a problem at all because we're working with a few hundred nanometer wavelengths. And so even a modest telescope of say 10 or 20 centimeters will give you an amazing resolution, something like 10 to the minus 6 radians, microradian. But suddenly when you're dealing with radio wavelengths, where you might have a wavelength of say 20 centimeters, doing it with a reasonable sized dish does not give you a particularly good resolution. And so, the diffraction limit for a dish of a couple of meter size would be about a degree in comparison. Or if we turn it around, actually, if we say, okay, an optical telescope of say 20 centimeters gives us a resolution of about half an arc second. If we want to do the same thing at 20 centimeters, and you do the similar ratios, you would need an 80-kilometer dish to achieve the same resolution. And so this becomes, in some sense, one of the most defining characteristics of radio astronomy, which is that we have to work around this diffraction problem. We have to deal with the fact that our resolution is not as good as an optical image. And I'll have an example of that in a couple of slides. And so the classic basic form of a radio telescope is the so-called single dish telescope, where you build a large dish. Here's in the middle here. This is the original first dedicated radio telescope from 1937 as a 9-meter dish. And so, classic form is you build a dish like this, or any of these. This is the Effelsberg 100-meter again, or the Parkes 64-meter dish. And so you build the dish as big as you can to improve the resolution by as much as you can, and the sensitivity as well. You're fundamentally limited, and so just to give a sense of that, on the right here is, this is the Pinwheel galaxy, I think, M101, as seen by Hubble, beautiful spiral galaxy. And on the left is an observation by the 100-meter Effelsberg telescope, which is one of the biggest telescopes, radio telescopes in the world, and it's observed at a moderately high frequency of 5 gigahertz. And this is the resolution you get. It's, you can see some spiral arms, one very bright. There's kind of a hint of one up here, but it's not very satisfying, is it? But we can cheat. There are ways around this to some degree. And I think this is really cool, so I actually wanted to spend a minute or two on this. And so if you sort of go back and think about dishes, the idea being that you have some wave coming in, reflecting back, and it all gets reflected back into the focus, such that it's all in phase. The shape of the dish dictates that. So all the electric field of this wave at every point is adding together at the focus. And so could you not accomplish the same thing by taking a large dish and replacing it by a whole bunch of little dishes or smaller antennas, and then just adding the voltages together, right? I mean, because if your antenna is converting the wave into a voltage, and you can either add the wave together and then turn it into a voltage, or you could turn it into a voltage and add the voltages together, and it should work out the same, yeah? And it turns out this does work. And so, and you don't even have to have like a solid filled-in array of smaller dishes or antennas. You make this a little bit sparse. You lose sensitivity, but it turns out that the resolution still depends on the distance from the furthest ends of your array. And so instead of talking in terms of the resolution as the wavelength over the diameter, we can talk about the resolution as the wavelength divided by a baseline between the two furthest apart antennas in the array. And so this works. And so as a result, you don't need to build a singular giant dish. You can make do with one of these kind of arrays of smaller systems. And so this brings us back to Lofar, which I introduced a moment ago. And so yeah, here's a somewhat sharper view or close-up of one of the Lofar antennas. It is 4 wires held in place with elastic bands, connected to the central stick, and in this black cap is a little amplifier circuit. And so 4 antennas feeding this little amplifier circuit, and then it has an output cable that goes underground into a control box in the back. And that is one part of this radio telescope. It's just literally that simple. And so what they've done is they've taken arrays of 48 or 96 of these sticks and wires, like 48 to 96 of them, and they all feed into the same control box, and they can add together those 48 or 96 antennas together to get a combined signal. And it works. And as you can see, it's not filled in, but it basically simulates having a dish that is, what is the size of this, 30 or 40 meters across, I think, without having to build anything expensive or complicated or movable. Because there's a second trick to this, which is, so the previous diagrams were talking about light coming in from straight above, or a wave coming in from straight above. What happens with a signal coming in slightly from the side? And so what happens then is this wave will hit each of the antennas at a slightly different time, depending on where the antenna is. But what you can do is you can simply add a time delay in your electric circuits. This is something that we know how to do. And so you can add a time delay to the circuit of each of these antennas such that the total travel time of the wave plus the voltage signal is the same for each of these, and then add them up, and they're still in sync. They're still synchronized, and so they still add up, and everything works. But, and now here's a really neat trick. What if you digitize the signal when it comes in, create copies of it, and then each copy can have a different time delay? Now what you do is you can adjust the time delay to look in any direction you want. You can basically pick a look direction, figure out what time delays you need to be sensitive to that, set up your computer to put in those time delays, make as many copies as you have computing power for, and you can look in as many directions as you have computing power for. And in the case of the Lofar array, the initial setup that they built for it is they can look in 488 directions at once. Yeah, it is fantastic. I love this telescope. I did my PhD with this telescope, and it is amazing. So this is the power of computing technologies. It's basically taken all of the analog optics, like all of the effects that happen by having a big dish, all the focusing, and then the problems of having to move the dish, and they've moved all of those effects and all of the physics and all of the problems into software, because software is easy in comparison, or at the very least, once you have the software, it's cheap to run.
I would like to interrupt here. Won't we have a spherical symmetry problem? Like if we want to observe something that's let's say right now I'm focusing at something which is at 180 degrees, and I want to observe something that's at same elevation at, let's say, at 0 degrees. Won't it be difficult to measure because the phase difference or path difference would be same for both of them? Because they are essentially...
Okay, I think I can see what you're getting at. And it's actually not a problem. So, I mean, in the 1D example illustrated here, is you can imagine a wave coming in slanted one way or a wave slanted in the other way, and the time differences end up being opposite, essentially, for a particular set of antennas. And then, of course, you have to do this in 3 dimensions ultimately, and so you can, for any given look direction, the time of arrivals to all of the antennas is well determined and it's unique. It's a unique function of the look direction. And so you can uniquely define a set of time delays that would correspond to one direction.
Okay.
Yeah. There are a couple of other problems, like the fact that other directions will not always be completely out of phase, because you can have, and this is getting into the weeds a bit, but is you run into problems sometimes where you always set it up so that one direction everything adds up in phase, but you can have a problem where other directions simultaneously you get partial cancellation from things not being in phase, but it's not 100%, and so you get something like 10% sensitivity, say. So you're 100% sensitive in one direction, but you're still like 10% sensitive to another direction. And so if you have a signal that comes in, it's difficult to differentiate between the signal has X brightness in your look direction, or it's 10 times brighter in the other direction, where you have 10% sensitivity. And there's a whole process of that. That's kind of a more advanced topic.
Another question which I want to ask is, like in this interference, we assume that sources are coherent, right? In simple cases. But
yes.
But in astronomical sources, can we assume this? Like every source is coherent with, or there is some changing function?
Yeah. Wow. So yeah, that's a really good question. So we can assume this comes into something called the quasi-monochromatic approximation, which I've actually lectured on before. And so if you start in the limit of a single frequency, so a single frequency just is coherent, like because there's nothing to allow it to decohere. And so for a single idealized monochromatic signal coming in, everything works fine. Real signals are not one frequency; they're a mixture of frequencies. But if you set up your telescope such that you can break the signal into narrow frequency channels, each narrow frequency channel will be coherent on some time scale depending on how wide it is in frequency. So the narrower you make your channel in frequency, the longer its coherence time. There's this, it's sort of a uncertainty relationship.
So we can tune that with software.
Yeah, essentially, yeah. When you some of it is in hardware when you set up the channels, channelization and bandwidth and stuff. But yeah, it's essentially it's taken care of in the engineering of the telescope. Let's say it that way. Is you can set it up such that you have some coherence time, and you can work within that for combining the signals, and that works fine. And so it does produce some interesting challenges to make sure that everything is synchronized to within that coherence time, but it doesn't introduce any problems in that sense. That was a very good question. Thank you. Okay. So yeah, so this system of adding together multiple antennas to get better sensitivity and better resolution is called a phased array system. But there is a slightly more sophisticated trick we can even do, and this is interferometry. So with the phased array, we were adding together signals from two or more telescopes. With interferometry, we end up multiplying them together or correlating them. And so this is effectively asking the question when we do the correlation of how similar or how synchronized are the signals that we're measuring with the two telescopes. If you do this pairwise for every pair of telescopes in your array, and you're essentially asking the question of how synchronized are these? And what that tells you is if they're synchronized, that tells you something about what direction the emission is coming from, because based on sort of phase relationships between. I won't get into the full details of how this works because the mathematics is a bit of a mess. But long story short is by combining the signals in this way, you come up with a better localization, a better sense of where the signal is in the sky than you do with a phased array system. And so a phased array, you pick a direction, and the telescope then tells you how strong is the emission in this direction. The power of an interferometer is you don't pick a direction, is you just detect everything. And the interferometer tells you in some vague sense, how strong is it and where is it in the sky? And so this becomes a much more powerful tool for imaging or mapping out large areas of the sky. And so, yeah, I have previously lectured on this, and it takes hours to actually cover the full theory of how and why this works. But,
can you elaborate on what you mean by synchronization? Like, what kind of synchronization are we talking about?
So interferometer is essentially measuring the phase relationship between the two signals measured at any pair of telescopes. And so it's telling you, are these signals, when I receive these signals, are they in phase? Both telescopes receive the same phase at the same time. Is one of them phase shifted by some amount, in phase, out of phase, anti-phase, etc. And this phase relationship gives you some information on what the location is in the sky, because different locations in the sky will, depending on the position of the antennas, be in or out of phase.
Got it.
And yeah, and so in some sense it becomes a game of, okay, this direction will be in phase for this pair of telescopes and out of phase for this other telescope. Is this what we measure? Yes, no, and then you can sort of work out what direction the emission has to be based on what combination of phase differences you measure.
And all these calculations are going real time, like when we are observing and all. Is this calculation going on real time?
Yes, essentially it can be done. So not all of this integral. I really don't want to get into these integrals, but not all of this has to be done in real time. The actual measurement in real time the measurement of the phase relationship is done in real time, and that's really easy because it's basically a multiplication and an average. The inverse process of working out the directions is not real time because that is computationally expensive and it requires many measurements. And so I guess the slide basically says what I've already said, which phased array is just adding. The interferometer is doing this correlation process for pairs. And so, for those of you, I guess, who have a little bit more mathematical background, each pair of antennas, each baseline, is essentially sampling one part of the Fourier transform of the sky. And so when I did this, what I just said about the sort of phase differences and the how different phase differences correspond to different possible positions, it turns out all of this is described by Fourier transforms. And so what we ultimately have to do then is make as many measurements as we can of these correlations of different baselines, and that fills in our information on this Fourier transform function. And what we do in the end essentially is invert the Fourier transform to create an image of the sky. So the underlying physics is where is the emission on the sky. Our measurements are sort of the Fourier space, and then we invert that and we get back a measurement of the image, the distribution of things on the sky.
Can we relate the phase differences as the Fourier coefficients? Like, is this what is essentially happening?
Yeah, exactly. So it is complicated and weird, but it works. It absolutely works. And this is what makes interferometry so amazing. It seems so bizarre that you can just take two signals and multiply them together and somehow get something that tells you about the entire area of sky that you're measuring. But it's amazing. I always think, like, mathematically, it's such a weird and subtle thing, and yet people have figured it out. And so interferometer systems are basically combinations of many different antennas or many different dishes, which are then, each of which gives a signal that can be combined through this correlation operation. And so, this top one is an example of a telescope in Western Canada, which is a seven dish array. And then the bottom here is a 27 dish array, the very large array in the United States. And so with these kinds of systems, you can image an entire chunk of sky in a fairly efficient way compared to scanning, I guess, with a phased array, where you adjust. With a phased array, you have to adjust the time delays to do every direction one at a time, essentially. And so the power of the interferometer is it lets you do an entire region of sky in one go, with less movement, I suppose, or with somewhat better precision. And of course, you can actually combine these two processes together, the phased array and the interferometer. And this is what Lofar does, where Lofar has this combination of the individual stick and wire antennas and the groupings of 48 of these. And then each group of 48 is phased together with some number of look directions. And then the different stations of these are combined as an interferometer. And so this has the net effect of the phased array gives you very good sensitivity because it has many antennas. And then the interferometer aspect of it gives you very good mapping ability. And so this in the case of the Lofar array, this is done using arrays throughout the Netherlands primarily, but also arrays throughout the rest of Europe. And so you can imagine, this is an old image. There's actually a bunch of new stations out in Poland now. And so you can imagine what I said before about how the resolution goes as wavelength divided by baseline length. And so you can imagine baseline length going from, actually there's a station in Ireland now. So you can imagine going from Ireland to Poland is a couple 1,000-kilometer baseline. And so this telescope is able to achieve amazing resolutions by having this sort of 1,000-kilometer separation between stations. And in the case of Lofar, it's because they're going to very long wavelengths that this becomes important.
So we are essentially having sets of phased array as an interferometer. Like, is this what's happening here? Okay.
Yeah, I mean, from a signal processing perspective, the phased array, once everything is added together, you have a single signal which acts like a single dish or like a single antenna. And so you can then take the phased array output and process it however you like, including as an interferometer, treating it as a signal for an interferometer. And so Lofar has this amazing flexibility where you can do both at the same time and sort of get advantages of both, which is really quite enjoyable. And so, yeah, I thought this is an example of actually a Lofar image that I made during my PhD. And so this is in the center here. This is a nearby galaxy called IC342. It's a spiral galaxy. And then you see a whole number of other objects here. And so each of these other things in this field, each of these points, is not a star. This is not an optical image where you'd expect to see a lot of stars. In the radio regime, stars are very faint, but galaxies tend to be bright. And so each one of these points is a radio bright galaxy in this particular chunk of sky. And so, yeah, and then one very nearby galaxy. There's actually a really faint smudge here, if you can see my mouse. That's actually a dwarf galaxy that's comparatively nearby. And then on the right side, this is sort of a double jet radio galaxy. I'll show some better examples of this later on. And so in the radio regime, we are really mostly looking at galaxies rather than stars to a large degree. But I'll come back to that in a bit. So I guess, finally on the radio telescope end is interferometry lets us do some amazing high resolution things. We can take it even further with the development of a version called very long baseline interferometry. And so normally in interferometry, you get the signals from each telescope or each antenna and you combine them in real time. But you don't have to. With our, we have the ability to store the signals in full detail so that they can be combined later. And these days, this means many multiple terabyte disks to get the data fidelity that we want. But it is possible now to record simultaneously with telescopes many thousands of kilometers apart, store the data in a way that is properly synchronized to sort of nanosecond level timing synchronization, and then ship the data to some central computer and do all the correlations afterwards. And so this really lets you take advantage of the full distance, I guess, the many thousands of kilometers to get them the best resolution. So with these kinds of systems, you can get a resolution better than any kind of optical system. As you can essentially create an interferometer that acts as though it were a telescope the size of the Earth. Essentially, you can see this. This is now tens of thousands of, or more, well, more than 10,000 kilometers separation between these antennas. And so you can do some really amazing things, and I'll have more on that in a couple of slides. So yeah, any other thoughts on or questions on sort of the telescope side of things before I jump into a couple of science applications? All right. So yeah, so I've picked out a couple of aspects of radio astronomy science that I think are both either really big or really interesting in terms of my own perspective and biases. So one that I already mentioned quite a bit is how you can use spectral lines, atomic and molecular spectral lines, to study the behavior of that material. And so you can actually learn quite a bit. You can work out the mass of how much gas there is, how much atomic and molecular gas, velocity from the Doppler shift, but also things like density, temperature, as well as sort of the turbulent velocity, not just how quickly the gas is moving as a whole, but also how much it's mixing and how quickly. And then also the composition, which I discussed a bit about, what kind of atoms, molecules are present in different nebulae or different environments. And so there's a lot that's been done to understand just the evolution of the interstellar medium and the evolution of gas and how it behaves over so the star formation process and the star death process. Yeah, another aspect is pulsars. Quite famously, are these sources that produce pulses of radio emission on timescales of anywhere from a few milliseconds to several seconds, and do so completely periodically for very long periods of time. And through studies of these, we now know them to be neutron stars producing concentrated beams of radio emission. And then as they rotate, these beams of radio emission periodically shine towards us. And so pulsars are amazing just in terms of how much information we've been able to get from them, and how precisely we've been able to measure them is because they're periodic and we can sit and measure them for long times, is we can learn a lot about not just themselves and how they're spinning and sort of the size and such of the source, but they can also be used essentially for timing on very large scales. And so combine pulsars with modern atomic clocks, and we can measure the time of arrival of pulsar signals on scales of nanoseconds. And what this lets us do is it allows us to understand the motion of the pulsar incredibly well through I guess, essentially Doppler shifting, or the time of arrival of the pulses. So like the motion of the pulsar, whether the pulsar is in a binary, whether it's moving around due to things like, in this sketch, you're talking about supermassive black holes. But any physical phenomenon that adjusts the time delay or the time of arrival of pulses, including gravitational waves on enormous scales between us and the pulsar. And so there have been pulsar timing projects to try and measure giant gravitational waves, like multiple parsec or light year long gravitational waves moving through space, because these gravitational waves will stretch and contract space by a very tiny amount. But if the space is slightly smaller, then suddenly pulsar signals passing through will arrive sooner. And if the space is stretched a bit bigger, the pulsar signals get delayed slightly. And so by doing these kinds of very, very careful timing measurements, people are hoping to detect very large, very slow gravitational waves. And so that's a very active set of projects these days.
What kind of time scales are we talking about when we say like expansion of space and contraction? Like what kind of time scale are we talking about? Like when we detect something like that, like what's the usual time difference?
Yeah. So the pulsar projects are looking for gravitational waves that have a periodicity of several years. is sort of what they're targeting. And so they're looking at gravitational waves where it's a several-year cycle of sort of stretching and contraction as the gravitational waves passes through the space between us and these pulsars, or passes through the proximity. Basically, even if these waves pass through the Earth, because they're also using multiple pulsars in different directions. And so the hope is that, they haven't actually detected these yet, but the hope is that they'll be able to detect essentially some set of pulsars should be moving closer and some set of pulsars in the other direction should be moving away. And that tells us that, hey, there's a gravitational wave passing through the Earth with this particular orientation of stretching and contracting. And so that's the goal. And to do that, they figure they need data basically on sort of 5 to 20-year timescales to be sensitive enough and to basically see enough cycles, I guess.
Okay.
And so these projects, I think these projects are about at the 10-year mark now. So we're kind of halfway, and there's starting to be some interesting hints that they might be detecting something. So it's an exciting era for pulsar astronomy right now. Yeah, so I mentioned radio galaxies a couple of moments ago within that Lofar image. And so galaxies are intrinsically very bright in the radio. They produce a lot of synchrotron radiation in particular. And so these can be used to study aspects of the cosmic ray population or the magnetic fields in galaxies, but also things like jets, and particularly so AGN, active galactic nuclei, are the supermassive black holes at the centers of galaxies, and particularly these are ones that are actively accreting or absorbing matter. And so the process of a black hole absorbing material produces a lot of radio emission, amongst other things. And so there's been a lot of studies of these supermassive black holes, but also, and this is something that I always find really cool, is as a byproduct of absorbing material, black holes tend to produce these jets, these spears of material shooting out in opposite directions away from the black hole. And in the case of supermassive black holes, these jets shoot out off into intergalactic space, millions of light years, until they eventually get stopped from colliding with intergalactic material, intergalactic gas and plasma. And so what you get then is when the jet finally gets slowed to a stop, essentially, by the intergalactic gas, you get these hot spots, and you get these huge, enormous lobes of emission and material that's been shot out from the black hole, out from its host galaxy, off into intergalactic space. And these show up in X-rays and in radio emission. They do not show up significantly in the optical. And so these are things that you cannot see with your eyes. You can't detect them with a classic optical telescope, because you need technology to know that these exist. You need a radio telescope or you need an X-ray telescope, and I find that really amazing. You know, stuff that we never would have known was out there until we developed the technology to see it. So yeah, radio astronomy also does contribute to cosmology in various ways. And so the classic cosmic microwave background map, this is the one from Planck. These are done from satellites to avoid even small amounts of interference from the Earth. But a lot of these projects rely on having ground-based radio measurements to help understand whatever kind of contaminating signals may be present in these kinds of measurements. But there's projects associated with something called the epoch of reionization, which is the very early universe. If you think about the very early universe, where first everything was very hot plasma, and then it converted to neutral gas and produced the cosmic microwave background. And then the first stars began to form, right? The gas began to collapse. The first stars, the first galaxies turned on, started spitting off ultraviolet emission, and started reionizing gas. And so if you were to go looking at, say, the 21 centimeter hydrogen line, right? Hydrogen gas anywhere in the universe gives off this 21 centimeter line, but it gets redshifted because of cosmology effects. And so in the early universe, there should be all of this highly redshifted hydrogen gas emission. And then as the galaxies started to form and you started to get ionization, converting the neutral hydrogen into hydrogen plasma, you should start to see holes appear where galaxies are converting the neutral gas into the plasma. And so there are projects to try and measure this in the very early universe, in the first few million years after the cosmic microwave background was formed. And so this will help us to understand when did the first galaxies form and the first stars, and how quickly did they form, and how big were they, and then how did that whole process go. And so there's a lot of very active projects, but this is a very challenging thing because you're trying to look at hydrogen signals from essentially across the universe. And so that's a very, very active and very exciting set of projects that's being done. Supernova remnants are a really big, I mean, they're not big, but they're a fun, I guess, aspect of radio astronomy. So supernova, of course, very famously, very bright exploding stars can be seen in the optical. But after a few thousand years, supernovae stop essentially glowing in invisible light, and yet they keep producing radio emission for tens of thousands of years. And so there's a lot going on to try and understand what happens to a supernova, after thousands of years. And then also how does the supernova shockwave start to blend into interstellar medium, into the interstellar gas? How does that process work? And so I have colleagues who are working on that. And you can even see supernova remnants growing in real time. So there's a video, I won't open it here, but you can find it. You can either look for supernova 1987A on YouTube, and there's an animation that one of my coworkers made where you can detect over the last 30 years how the supernova is slowly expanding out. Sort of the shock wave is expanding into interstellar space. So there's a lot of cool stuff going on there. I mentioned earlier the very long baseline interferometry. And so that's been made quite famous in recent years because of the Event Horizon Telescope project, the first project to image the event horizon of a black hole. Right here, of course, is the very famous image. And this was done by pushing radio astronomy to its very furthest limits. And so doing the very long baseline interferometry with the longest possible baselines that you could get, and also because they needed this amazing resolution, right? And the resolution is wavelength divided by baseline length. So they went for the longest baselines to make the diameter, or to make the denominator large in that fraction. And they went to the shortest possible wavelengths, the highest radio frequencies, in order to minimize the numerator in that equation, to get the resolution to the smallest possible number, to be able to see the smallest thing that they could possibly do. And that's what it took. And so it was an incredibly challenging project, and I have a lot of friends who have been working on this, and it's incredibly difficult pushing the limits of what radio astronomy can do. So yeah, finally, one that's very near and dear to my heart. This is what I work on, which is cosmic magnetism or galactic magnetism. And so using radio astronomy, and particularly by measuring the polarization of radio emission, so the polarization of the light, it's actually possible through a couple of different physical processes to measure the magnetic fields in interstellar space. And so on the left here, here's an example. This is the Whirlpool galaxy again, where the overlaid vectors here are indications of the magnetic field direction in the disk of this galaxy. And so you can see how the magnetic field also, like the galaxy, does kind of have a spiral orientation, although when you do a very detailed analysis, the spiral pattern of the magnetic field doesn't actually line up that perfectly with the actual spiral pattern of the spiral arms. There are differences, and there's some interesting complications there. And to some degree, we can even measure this in our own galaxy. This is a paper that I did 10 years ago now, trying to work out the magnetic field directions in the Milky Way galaxy. And there's some complicated things going on here where most of the magnetic field is going clockwise, but there are some sections of counterclockwise magnetic field. And what's up with that? That's all weird. So there's a lot of stuff being done in that field, and that's what I work on primarily. So I've gone quite long. I don't know. We didn't put a time limit on this, but I'll just end with this picture of me standing underneath one of the dishes at the Very Large Array. It's a 25-meter dish. And for any of you who are interested in sort of some of the more detailed explanations for some of these aspects, I taught a course about a year and a half ago on Introduction to Radio Astronomy. It was 8 lecture hours, and so it gave me a bit of time to introduce the concepts in a bit more detail. So if you're interested in that, it's available online at that website. So yeah, that's all I have. Thank you very much.
Thank you for seminar.
Thank you, Cameron, for this amazing talk. I have a few questions. Can you move a few slides back? Like where you showed the Event Horizon Telescope. Yeah, yeah, here. So, if our major concern for the resolution is the distance between two telescopes, which is maximum, right? So, why don't we make just 2 telescopes which are furthest away? Like, why are we having so many intermediate telescopes? Is this for the signal to noise ratio, or what's up with that?
It's partially for the signal to noise ratio. There are some additional complications in terms of if you only have the longest baselines, your image quality tends to suffer, and there gets into some technical aspects about different Fourier scales and such. But so you essentially want a mixture of the longest and sort of middle length baselines in order to get the best possible image quality. So that's part of it, and an additional aspect in terms of trying to get the telescopes as far apart as possible is first of all, both telescopes need to be able to see the target at the same time, and so you can't put them, if you put them on exactly opposite ends of the Earth, which I guess in this case would only be halfway to the edge, and you set them to look at a target, they would only be able to observe if the target is also kind of on the celestial equator. It would only be above the horizon for a few minutes before one telescope is now below the horizon and the other is above. And so that kind of creates some problems. And in the case of the Event Horizon Telescope, because they need to push to the highest frequency or the shortest wavelength, they have the water vapor problem from the beginning. And so they can only operate at sites that have sufficiently high altitude or low water vapor that they can actually work at that frequency.
Okay.
And then the other aspect is budget, is Event Horizon Telescope is not building new telescopes; they're using existing ones, and so there's limits. Okay, where have the telescopes been built in the world, and which ones can we use? And so, I mean, the Event Horizon Telescope team are working on getting money for additional telescopes. I know that they want to build one somewhere in Africa, I think, to try and fill in the network a little bit more. They worked out for whatever reason that would be an ideal location. So that's something they're working on. But ultimately, it's budget.
Also, an unrelated question, kind of, but like you showed, like we have calculated what all elements corresponds to which emission and absorption line. Like how is it actually worked out? Like first I have a data. I am only seeing like spikes and all. So how I know that this energy level corresponds to that element, and when I am having some Doppler shifting.
That is a really interesting problem. So there's a couple of steps in that. The first one is that there are databases of known lines done, which are measured often through lab experiments. And so we can do lab experiments here on Earth. Take a particular molecule, put it into a vacuum chamber, shine it with lasers, and work out what its spectrum is. I actually spent a summer working in a molecular spectroscopy lab. And that was a cool experience, is doing those kinds of measurements and measuring different molecules. So we have databases of that, and so that's one starting point. But as you said, the Doppler shift kind of adds the problem in the sense that now all the lines have moved by some unknown amount. And so what's usually done is you have to look for patterns in the lines where you can say, okay, so I don't know if this is legible or not, but for example, there are multiple lines here that are marked SO2, sulfur dioxide. And so in that case, you can say, okay, I think, if I think that this particular molecule is present, I can take all of its known lines and I can shift them by different amounts to see, if I adjust the Doppler shift at some point, all of these lines should like match up. And so there is some pattern matching algorithms that are involved. And it also gets complicated by the fact that, the different lines can have different strengths, or they may be present or not, depending on the temperature and the density of the molecules. And so that's part of the reason why there are so many faint lines here that are just not identified, because this is a difficult process. And so they've been able to do it with some simple molecules and some of the ones they think are more likely, but there's still so many lines here yet to be identified.
Okay. And one more question I have related to Event Horizon Telescope. Like, let's say, or phased array telescope and interferometers in general, like we are using phase differences to measure like what's the object is like, right? So what if the object is very dynamic in nature, like it's changing its radiation pattern in, let's say, in millisecond intervals, or even smaller scale?
Yeah, absolutely, yeah. So, and that is happening. Yeah, that is happening. Yeah, and so any interferometer, including a very long baseline interferometer, has to put in time delays, essentially. Actually, I didn't discuss it, but there is sort of a time delay here called the geometric time delay, which is associated with the difference in arrival time at the different antennas. And so you do have to actually correct for that, and include a delay in some of the circuitry, or when you do the combination in the VLBI case. And so you have to account for that in a way so that you are sort of comparing the same signal as much as possible, and you correct that in a known way such that you know how your correction has affected the phase difference. And so you can then, when you work out all the phase differences, you say, okay, here's the measured phase difference, plus I can add the effect of what I did to make it all work out.
So we can essentially correct for those extremely dynamic sources.
I mean, essentially in the sense that we can make sure that we are correlating the same signal. So if a source is bright at one instant and dim, a fraction of a second later, we can make sure that we have correctly matched bright with bright and dim with dim. In some cases, it depends on the instrument and how it's set up as to whether or not you would notice very short-term variations. Not every telescope is configured. Some of them will do a lot of time averaging, depending on what kind of processing you want to do and what your end goal is. In some cases, yes, you can measure fluctuations, and so I should have actually added a slide on fast radio bursts, because those are fluctuations on millisecond timescales that have been detected in some systems.
Okay.
And so that can be done, yeah.
And one more question I have is, like, contrary to optical telescopes, we don't have a CCD where we are having individual pixels, right? Each radio telescope is just one pixel. So how we are correcting for, let's say, hot pixels and cold pixels, like if we have such things in radio telescope? Like, let's say if a telescope is overreacting to some, like, how do we correct for those?
Yeah. So because it is one pixel, as exactly you said, is sometimes that pixel will be a hot pixel or a cold, or have different sensitivity variations, and so there is a whole process of calibration, which has to be gone through, and it depends. The calibration process depends a bit on the telescope and how it's configured, but I mean, in the general cases, you have a source of known brightness, and you observe it, and you say, okay, I know the brightness of the source. Here's what I measure, and so there must be some gain factor, essentially, that I have to account for in order to make the two numbers line up. And then when you do that on a known source, and then you can go to a new source and do a new measurement and be reasonably confident that your brightnesses are calibrated. And so that is a process, and there's a lot of checking and different ways of dealing with that, especially if it's time dependent or frequency dependent or whatever. Yeah.
Okay. And how we correct for errors? Let's say, like, radio window is like quite literally like 100% of the light comes, like, but we still have some problem, let's say, from water molecules. Like let's say in the line of sight of one telescope, we are having greater density of H2O molecules and all. So these are some like random errors. How can we incorporate these in our observations? Like, do these actually affect our results or not? That should be the first question.
It can affect the results. It can affect the results. I mean, the calibration process that I mentioned, if you're working with an interferometer, you can calibrate on a per dish or per antenna basis generally, and so that will allow you to correct for differences between antennas, and to some degree, I mean, particularly things that can vary in time, like you can have like you mentioned the water vapor. It's actually, thinking about it as a side note, at high frequencies, water vapor can cause phase shifts in the signals essentially, and so or even not necessarily the water vapor, just the atmosphere. Even though the atmosphere is transparent, it can still introduce phase shifts, and so you can get results that are a little bit like twinkling of stars in the radio. And to some degree, this can be calibrated on some time scale by radio systems. And so, like particularly in higher frequencies, you have to do a calibration every, say, 15 minutes, where you go to a source that you know where it is and what it looks like. You do a quick interferometer measurement, like a minute or so, and you say, okay, these phases I'm measuring are not right, and so I have to introduce corrective terms for those phases, and then you go back to your target and you apply the same corrections. And so this can drive down the error budget. It can't get rid of it entirely, but it does drive down the error budget.
So this will also affect, like, let's say you talked about like fast radio bursts. So these can be affected by this, right? Because we have to take into account the error. We have to do integration over greater time scales, and when we do that, we essentially lose the fast changing signals, right?
Yeah. So that's part of what makes fast radio bursts so difficult to study. Is you can't take advantage of time averaging to boost your signal to noise. Is you have one event, the signal to noise is whatever it is, and there is very little you can do to improve it. You can do a few things, like you can average over frequency, for example, and you measure as much frequency bandwidth as you can simultaneously, and then average over that, and that's very common. But yeah, ultimately, with something like a fast radio burst, is you just have very limited ability to improve your signal to noise.
Okay. And who are designing these systems, like software correction systems and all? Like, are these done by radio astronomers, or these are done by some computational physics and software engineers?
Yeah, I mean, it's a bit of a mixture. So I have worked on some of these software systems or aspects of these myself, and so it's a combination of radio astronomers who sort of know the radio astronomy aspects, usually in partnership with software developers and so people with more programming expertise, to try and work out how to optimize the computation aspect of it. And so it's really depending on the project as to who they have on staff partially, but I mean, for the really big projects, yeah, you start with a radio astronomer who defines the equations and what the inputs and outputs have to be, and then you go to your software developers. It's like, how do we do this efficiently?
Okay, thank you, Cameron, for answering all my questions. I won't bother you anymore.
No, please do. And anyone else have any questions?